Okay, now we have already just seen that a vector can be expressed in terms of or can be resolved into two components along any two vectors. Now let us consider a vector A here. And let us consider that these are the coordinate axes. This is x-axis and this is y-axis. So we can always express vector A in terms of two components along x-axis and along y-axis. Let's drop this perpendicular here and drop a perpendicular from here to the y-axis. Then this length will give us the AX vector, and this will give us the vector AY. So that AX vector plus AY vector equals vector A. Clear? Simple resolution of vectors. Now, what we notice from this geometry, let's call this origin, that let's say vector A makes an angle of theta with the x-axis. Then O, P, Q, R. Okay. Then this length OP is equal to, is given by OQ cos theta or A cos theta, and the length OR, which is equal to PQ, will be given by OQ sin theta, this one or this one. So this is A sin theta. So what we have seen is that we can always express any given vector along two mutually perpendicular directions. And please mind this is going to be very, very important. The rectangular resolution of rectangular components or resolution of vector into two mutually perpendicular directions is going to be very, very important in the coming analysis and the entire physics, not only in class 11 but also in class 12 when we will be discussing electrostatics and all. This is going to be very, very important. So you have to pay utmost importance to this or understand this very clearly. Now any given vector AX can be given by its modulus multiplied by a unit vector in the direction of the given vector, right? Now conventionally the unit vector along the axis, along the x-axis, is given by I cap, I and the caret for the unit vector. So this can be written as AX modulus of x AX into I cap, and AY similarly can be given by AY into unit vector along y-axis, which is given by J cap. So vector A is equal to vector AX into I cap plus vector, modulus of AX, and AY into J cap. But AX and AY, this length OP is AX and length OR is AY. So we can write this is equal to A cos theta I cap plus A sin theta J cap. Clear till now? Now, what is the magnitude of A? Vector A, or magnitude of vector A, or square of that, can be given by, from the formula, square of this plus square of this plus 2 this magnitude into cos theta, right, where that theta was the angle between the two component vectors, that is a, y and ax. Let us say this will be ax squared plus ay squared plus 2ax ay. Just consider this as ax as a, ay as b. So a square plus b square plus 2ab cosine of theta. Now theta is the angle between the given vectors. Remember, vector a and b. In this case, vector a is ax and vector b is ay. So we have the angle between this. Since ax is along x-axis and ay is along y-axis, the angle between them is 90 degree, right? So we have cos 90 degree. But cos 90 degree is 0, we all know. So what we will have is that it's ax squared plus ay squared. But ax we have found is a cos theta and ay is a sin theta. So we get a squared cos squared theta plus a squared sin squared theta. Fine. So a equals to square root of this. Fine. And this, of course, if we take the common, a square common, cos square theta plus sin square theta, and we will be left with a square or square root of this. Fine. And what is the angle? Tan of theta. From this diagram, tan theta is perpendicular, which is ay equal to a cos theta, and this is, sorry, a sin theta, and this is a cos theta. So we have ay by ax, which is a sin theta by a cos theta, which is tan theta. Fine. Are we clear till now? Okay. Now, if we move on and consider the three-dimensional case. See, up till now we have been talking about two dimension because our topic is motion in two dimension or motion in a plane. However, we know that the space, that as we know, is three dimensional. It has an x-axis, a y-axis, and a z-axis perpendicular to both x and y. So let us try and represent this here. So we have an x-axis, a y-axis perpendicular to x-axis, and a z-axis which is from this origin perpendicular and out of the board of out of the plane of the board. Now this we can represent in here as the z-axis. Please remember this is supposed to be perpendicularly out, but we have a two-dimensional plane, so we cannot draw that. So we have drawn it here. Now we have already seen is that the unit vector along x-axis is given by I cap, along y-axis is j cap, that we have already said, and the unit vector along z-axis, it will be given by k cap. These three unit vectors I cap, j cap, and k cap. These three are known as the orthogonal triads of unit vectors. Why? Because these three vectors are orthogonal. That is, I is perpendicular to j is perpendicular to k, and k is perpendicular to I. All three are mutually perpendicular to each other. So that's why they are known as orthogonal, and since there are three of them, so they are known as triad. So these three are I cap, j cap, k cap are orthogonal triads of unit vectors along x-axis, y-axis and z-axis respectively. Fine. So we can always resolve, as we have seen that we have been able to resolve a vector in 2 dimensions along x and y axis. We can resolve a vector in 3 dimensions. Say we have a vector from this origin and along this direction, say making some angle with the axis and also the z axis, like this or like that. Then we can always express it or resolve it into 3 mutually perpendicular directions along x-axis, y-axis and z-axis. How to do this? That you have to draw it a little bigger and more clearly. Alright, now let us consider a vector A in the 3-dimensional plane x, y and z. So what we do is that to find its components, what we will be doing, we first take the vector and from the head of the vector, let's drop a perpendicular onto the x, z plane. This is the origin, and this point, say, touches the xz plane at point T. So if we consider this diagram, then let's call this point P. In delta OTP, what we clearly see is that OT plus TP must be equal to A or OP. Why? Because this angle here is 90 degrees. So it's a little difficult to visualize, but say this is the plane. We had a vector like this. We have dropped a perpendicular here. So we are talking about this line, and this will be the vector A. Let us say on this plane we have this as vector A, and we have dropped a perpendicular from vector A onto the plane. So what we are left with? We are left with a right angle triangle O. This is point T and this is point P. So OTP and this is right angle. So we have vector OP. Sorry, let's take this plane. OP, that is vector A, is equal to vector OT plus vector TP. Okay. Now let's make some more drawings, in the sense that let's draw a line from OT to parallel to the z-axis. That is this line, and this will be perpendicular to the x-axis again. And let's say it meets x-axis at point Q. Similarly, let's draw a line from T to the z-axis. Let it meet z-axis at point R. Fine. Then if we consider this rectangle, this is the diagonal, this is one vector and this is another vector. So vector OT from this rectangle OQTR, this vector OT must be equal to OQ plus OR. So using these two equations, we get OP vector is equal to OQ vector plus OR vector plus this TP this TP is equal to this length S. See? Why this two? Because this forms a cuboid. So these sides, all these sides are equal. So OS must be equal to TP. So plus OS. Now OQ is vector X AX plus OR is a vector AZ. OS is vector AY. OP was vector A. So this is the resolution of vector A in terms of three components along x-axis, y-axis and z-axis. Okay. Now this is equal to AX into unit vector along x-axis plus AY j cap plus AZ k cap. Fine. Now to find the magnitude of this vector, what we will do is let's consider the delta OTP, this triangle, delta OTP, which is, as we have said, is right angle, and angle T being the right angle. So what we find is that using Pythagoras theorem, OP squared equals to OT squared plus TP squared. Also, if we consider the triangle OQT, which is again a right angle triangle having right angle here, it will give us OT squared must be equal to OQ squared plus QT squared. However, from the geometry, QT is equal to OR. So this is equal to OQ squared plus OR squared. And so if we substitute this value of OT squared, we get OQ squared plus OR squared plus TP squared. Now TP we have already found is equal to OS in the previous case also. So what we do is equal to OS squared. Substitute the value. OQ is vector AX. So in terms of magnitude, this is AX squared. OR is AZ, so AZ squared, and OS is AY, so AY squared. So OP squared, that is A squared, or magnitude of vector A squared, is this, or we can say is that magnitude of vector A must be equal to AX squared plus AY squared plus AZ squared, whole thing under root. Alright, if you like the video, then please like and share the video and also subscribe it. In the next video, we will be discussing about dot and cross product of vectors, and from there on we will also look at certain problems, and then we move into the motion in two dimension, that is how to use these ideas of vectors that we have developed over a few videos or few sessions, how to use these concepts into motion in two dimension. That will be our next topic. Thank you.